So we are starting with these questions from H.C. Verma, Laws of Motion chapter. (16), 21, 23, and 25. So just go through these questions. I will start with question 16 straight away. If anybody has any doubts from kinematics and laws of motion, also from kinematics also from H.C. Verma, please send it to me in text message. Okay. Then we'll come to the worksheet and other things also. Let's first complete H.C. Verma doubts. Okay, so let's go through question number 16. Okay, Laksh, we'll discuss those questions also. And Darsh, I have received your questions also in file format that you sent. I will just discuss them after completing all this. Right, so we have to show the reading of the spring balance inside an elevator, which has an Atwood machine, okay, attached with a spring balance and which is accelerated. So 16th question is basically about application of Newton's laws of motion in non-inertial frame. I can also show you how to do this in inertial frame, but it will be a little bit more complicated. Much easier to solve this type of problem is using concept of non-inertial frame. So let's begin with question 16. So we have an Atwood machine which is inside.
Your screen.
Yes? Oh, sorry, the screen is not shared. Okay, this one. Yeah, is it there now?
Yes, sir.
Right. Okay, so this is going up with an acceleration, let's say A naught, which is g by 10 in magnitude, and inside this we have a pulley which is attached to a spring balance. So basically what the spring balance ends up reading is the tension in this thread. The tension in this is, let's say, T naught. Then T naught will be the reading of the spring balance. So anyhow, now we have this system of two blocks which are given of mass 1.5 kg and 3 kg. So the easy thing to do here will be to place our observer inside the non-inertial frame, so that in his frame what he is observing is that the pulley is at rest, okay, and the heavier block is coming down with some acceleration A. The lighter block is going up with some acceleration A. So this acceleration is in the elevator's frame, which becomes a non-inertial frame. So now you can see that if this tension is T, we'll take this as a massless pulley. So the reading of the spring balance, which is T naught, will be equal to 2T. Okay. Now let's make the free body diagram of each of the blocks. We'll make it in the non-inertial frame, okay, which is going up with an acceleration A naught. So each of these will experience a pseudo force, which is opposite in direction. So these are pseudo forces. Apart from that, of course, there is the true weight M1G and M2G, and there is same magnitude of tension acting upwards. And in this frame, this one is going up with an acceleration A, whereas this one is coming down. So we have the equations that M2G plus M2A naught minus T is equal to M2A, and T minus of M1G plus M1A naught is equal to M1. So now very standard situation, if you just add these two equations, you can see you will get M2 minus M1 into G plus A naught is equal to M2 plus M1 into A. So we'll get this kind of a relation, like a standard Atwood machine relation, but G is replaced with G plus A naught because of the effect of non-inertial frame. So this here will become 3 minus 1.5 upon 3 plus 1.5 into G plus G by 10. Right. So this is becoming 1 by 3 into 11 by 10 G. This is the acceleration. So therefore now the tension T, you can see, is equal to, for example, if you pick up equation 1, from that you can see the tension is M2 into G plus A naught minus E. So you can see that the tension is equal to 3 multiplied with minus 11 by 3. That is further we can write this as 33 by 30 into 1 minus 1 by 3. This becomes 22 G by 3. This is the tension T. So therefore the tension in the spring will be equal to 2T, which will be 44 G by 3. Therefore the reading of the spring balance will be equal to 44 by 3. So there is a there is some calculation mistake I've made. I've taken 10 common here, not. So this is 33 by, should be, yeah. So I had taken 11 by 10 common. So this became this. Okay. So this is 2/3 into 11 by 10. Two-thirds will become 22 by 10. So this should be 44 by 10. Okay, that makes sense. Okay, so that should be the answer.
Sure.
Yes.
Sir, here we took the pseudo force because of the acceleration of the lift, right? Like lift was also
Yes.
accelerated.
Because whenever we apply Newton's laws, okay, or whenever we make a free body diagram in a non-inertial frame, then in that frame, that body experiences pseudo force, because of the acceleration of the frame and its inertia. Combination of the two things creates that force which is by an imaginary agent, but it's a very real force, and that's called pseudo force, right? So the formula of pseudo force, as you know, is the pseudo force acting on a body of mass m moving in a frame which is moving with an acceleration a naught, is given by this. So it's opposite in direction but equal to m a naught. So here a naught should be the acceleration of the non-inertial frame, not the acceleration of the body. It's the acceleration of the non-inertial frame, and m is the mass of the body.
Sir,
And this is, yes.
sir, can you explain me how pseudo force applied in this two box?
How
A and
pseudo,
B?
how
Mass.
pseudo force? Sorry.
Yeah, in this two mass,
Hmm.
mass one and mass two, how the pseudo force is applied?
So see the formula of pseudo force is written here. On a body of mass m moving inside a frame which is having an acceleration of a naught with respect to ground. This is the formula of pseudo force. Okay. So apply it to this body m1 over here. Its mass is m1, and what is the acceleration of the frame? A naught upwards. So pseudo force का direction क्या हो जाएगा? Acceleration के opposite. So it should be downwards. और magnitude कितना हो जाएगा? m1 into a naught. Understood this? And same thing on this block. This the m2 one also. So just one easy way to remember pseudo forces, like imagine you are standing inside a bus, which was initially at rest, but now it suddenly starts moving, so it accelerates forwards. So you will experience this pseudo force that acts on your body backwards. And the heavier your body or the heavier an object, the more the amount of pseudo force that acts on you. Or same way, if you're moving in a bus, which is already moving with some velocity, but suddenly it brakes. So as it brakes, it's decelerating. So your body feels jerked forward. No? So that happens because of pseudo force. So that's a very easy natural example to remember how pseudo force acts. Okay.
Sir,
Yes.
sir, in this question, you have taken M2 mass is accelerating downward, no?
Yes, because it's the heavier block. M2 is 3 kg, M1 is 1 kg. So it's natural that the heavier one will be accelerating downwards.
Yes, sir.
Understood? So see, it's basically the treatment is just like a regular attitude machine. But the difference is that had this lift been stationary or even moving with uniform velocity, then there would be only M1G and M2G acting downwards on the blocks. But now along with that, there is pseudo force. So it's like, because the lift is accelerating upwards, the effective weight of these blocks becomes more. Instead of just M1G and M2G, it becomes M1 into G plus A naught and M2 into G plus A naught. And
Yes,
that is a
sir.
normal thing. When you're if you're standing on a weighing machine inside a lift that's going up, you will not the reading will not be your true weight. It will be more than your true weight because of that same effect. Because pseudo force pushes you down, so you appear to be heavier inside that lift. So same thing is happening to both the blocks. The effective weight instead of mg, it is actually becoming 11 mg by 10 because your a naught is g by 10. So you can also just understand this way, that inside this lift what is happening, your effective gravity is becoming like g a naught plus g. So it's actually 11 g by 10. Okay, so naturally your acceleration will be m2 minus m1 divided by m1 plus m2, that standard formula, but into this effective g, which is this much. If you substitute that, you'll see you'll get the answer that we've discussed here. Okay.
Yes, sir.
Okay. So that's also effective way of understanding the question. So anyhow, so hope this is clear now, right?
Sir, so it means we need to solve this question only by pseudo force because of the acceleration of the lift, right? We can't.
Yes, you can also solve it using relative motion, but it will be a little bit more complicated. So when I'm discussing relative motion in kinematics, which will be the last thing in kinematics, I will show you the relationship between pseudo force and relative acceleration. So at this point of time, it's so one thing you can just simply understand that if you're seeing this from the ground frame, you will not see the two blocks having the same magnitude of acceleration because the pulley is also going up.
Yes, sir.
So then we cannot write both their acceleration same A in magnitude. So the question will become more complicated to solve. Hence, what we have to do here is we have to solve by. It's easier to understand it in the reference frame of the lift, which becomes a non-universal. Okay. Yeah, Mansi, I have received your message also. I'll be coming to your questions also. Okay. Don't worry, we have plenty of time today, so we'll cover everything. Okay, let's come to the next one. 21st question from HC Verma. Okay, so 21st question is basically to do with the concept of cross product. Okay. So it's not really so much about free body diagram and all that, but instead there is some kind of, you have to imagine this equation that there is some situation I've created where a force acts on a particle or a body or whatever, which is given by this formula, where v is its instantaneous velocity, but a is some kind of a constant vector. So this type of force is exerted in addition to gravity, where v is the velocity of the particle and a is a constant vector in the horizontal direction. So a is a constant horizontal vector. So let's just visualize this problem three-dimensionally first. So let's say this is like some horizontal plane, some kind of a horizontal plane. So gravity is perpendicular to this, like this. This is your vertical direction. So let's say we have drawn our reference frame such that, let's say, x-axis and y-axis constitute the horizontal plane. And gravity is along the negative z-axis or whatever. Okay. Now, since I am free to select my x-axis anywhere, as long as it's in the horizontal plane. So let's say I have selected the x-axis originally in such a way that my vector A was lying along the x-axis. It's in the horizontal plane. So in whichever direction that vector A was, I've just selected that to be my x-axis. So I can write the vector A to be ai cap. Okay. And therefore gravity is becoming minus minus g k cap in my diagram. Okay. And we understand that the xy plane is the horizontal plane. So that's how I've set my reference frame. And the z-axis is vertical. So now if I have any particle which is moving with some kind of a velocity v, what are the forces that will act on it? There will be mg acting. Okay. And now you can see that E, suppose you assume V is something like this and A is a vector like this. So E cross V will be, or V cross A in this case would be in the downward direction or whatever. But the net force on this body or this particle would be mg plus V cross A. This would be the situation. So it would be minus mg k cap plus V cross this thing. A I cap. Okay, so this would be the net force. So now I want the situation. Okay, I want the situation that what is the minimum speed of the particle so that it continues to move undeflected. Okay, so let's say the velocity of the particle is having all three components. Okay, now you might have guessed that this is not going to be correct. It should not have all three components if I want net force to be zero. But suppose I'm not making any sort of guesswork. I'm just saying that let's say the velocity has all three components, but I want the condition that the net force on it should be zero. Okay. Then I want to find what is the minimum magnitude of this velocity. So how we'll solve this problem? So I have to solve this equation that net force undeflected jara means acceleration is zero. Undeflected with uniform speed, that means this acceleration is zero. So I want net force to be zero because the acceleration of the thing should be zero. So that means the net force is okay. So my net force is becoming minus mg k cap. Okay. Plus, now let's write this out. Vx I cap plus Vy j cap plus Vz k cap cross product with AI cap. Now you might say that I'm solving a very specific situation where I have taken as if A does not have any Y component, it has only X component. But I'll say it covers everything because I was free to select the XY axis as I please, as long as it's in the horizontal plane. So A vector horizontal plane mein jahan par bhi tha, I've just selected that to be my X axis. Okay, so there's no problem with doing that. I'm not, I'm not eliminating any case in that. Okay, it covers all cases of the solution over here, of the general solution. So I want this to be zero now. Okay. So let's work this out. So minus mg k cap plus, now see, let's solve this cross product. So I cross k, gives what? X, Y, Z, and so I cross k gives minus j. So this will give us minus AVX j cap. So basically, you'll definitely see that I don't want any Vx component because I don't want any velocities component. Oh, sorry, I cross I, my mistake. So I cross I, the first term will be zero. I cap cross I cap is zero. So the first term will give you zero. Okay. Then the second term is J cross I. Yeah. So J cross I is minus K. Okay. So this will give you minus Vya J cross I, which is K cap. Okay. And the third term is K cross I, okay, which is J. So AVZ J cap. So this should be zero. So now put the vector together. So you'll see you have minus mg AVY K cap, right? And plus AVZ J cap. So this should be zero. So this is zero only if both these components are zero. So this thing also has to be zero, and this thing also has to be zero. Okay. So compulsorily we must have Z component zero. Okay. And compulsorily we must have Y component to be how much? Minus mg by A. So that means in general, what can my vector be? My vector v for this condition can be any Vx. It makes no difference what Vx is, but a specific value of Vy. Okay. And no k cap component. So in general, this velocity ensures that the net force is zero. Okay. Where Vx can be any value, any real value. Okay. So therefore, for mod V to be minimum, it should be mg by A. Okay. That is, Vx should be zero. And V should in that case become minus mg by A j cap. So this is the minimum speed condition for the net force to be zero. Okay. In general, we could have any speed like this, Vx I cap minus mg by j cap. So the necessary condition is that Vz must be zero. Okay. Vy must be minus mg by A. Okay. and Vx can be anything, including 0. Okay, so that's why the minimum condition is when Vy is that much and Vx is also 0. Okay, so this is, as I told you, it's a question all about vector algebra. Okay. So I'll just leave you to go through this for a moment. Okay. Then we'll come to the next question. So next we are doing, I think, 23, 25. 37 and 39 also. Okay. Okay, so 23 interestingly actually becomes a kinematics problem. I mean, of course, you're using Newton's laws in it, but you are also going to have to solve the equations of motion separately. So let's discuss.
Sir, in this question, I didn't understand what do we have to calculate.
We have to calculate the minimum possible speed with which you can project it so that its acceleration is 0. You understanding? There is one force that is acting, which is always vertically downwards, the weight, irrespective of how much velocity we give. ये mg wala force, it is a constant force. It makes no difference how the body is moving. But the second force that is acting on it, this one, V cross A, both its magnitude and direction depends on what velocity we are giving. You understood? No?
Yes, sir.
So there must be some minimum velocity that we can give it. I mean, minimum magnitude velocity we can give so that we will achieve the condition that this force F will cancel mg so that the net force will become 0. So that is the thing that we have to find, that what is this minimum speed with which we can project it, and ideally we should also find what direction we should project it in so that this condition is satisfied, that the net force should be 0. Okay.
Yes,
So
sir.
now, so what we do is first we end up solving that what kind of velocity is required for net force to be 0. So the general solution that we get is that we require this kind of velocity, that Vz component should be 0. It should not be non-zero. Vy component should be minus mg by a. But for Vx component, we can have any value. In fact, any value from minus to plus infinity. Okay. So any velocity of this type will do. So out of this entire set of possible velocities, which one I should select so that the speed is minimum? So if I want the speed to be minimum, obviously I want Vx to become 0, because the speed in general will become square root of Vx square plus this mg by a whole square. So now this I can take any value I like. So for this to be minimum, I should take this as 0. Got it now?
Yes, sir.
Okay, so now let's come to 23. Okay. You can take down the solutions and all later. I will send you the PDFs and the recording of the talk session fully, so don't worry. So question 23, you have this output machine from the previous question, which is 300 grams and 200 grams, 600 grams. Okay. Now what is happening? You're starting the system from rest. Okay. And 2 seconds afterwards, okay, now this is where the question becomes a little tricky. You are stopping the heavier block for a moment. Okay. The larger mass is stopped for a moment. So what does this moment mean? Moment just means an instant of time, a very, very brief interval of time. It doesn't mean one whole second or anything like that. Okay. So you're just stopping it and then letting it go at t equal to 2 seconds. So you can think like at 2 seconds, you just block the block M2, or you stopped it by holding it and released it immediately. So almost a nanosecond or a microsecond or something like that later, you just let it go. Okay. So let's understand the system right from the beginning. So let's say this is the initial state when the blocks were both at rest and you release the system. Okay. So this is my so-called t equal to 0. When the blocks are both at rest, but because the string is taut or it is tight, the moment you release it, okay, the weight of the heavier one dominating weight over the weight of the lighter one means that the string immediately develops this uniform tension, right? and the system develops this uniform acceleration. So as long as I don't disturb the blocks, this acceleration will remain constant. And you know the formula for this. And now you solve so many equations like this, so you can see that it's like this. So this case, this was 600 and 300, right? So basically, this will become 1/3 of G. When you see the masses are in 2:1 ratio, you'll always get like that. M1 and M2 are in 2:1 ratio, so this factor will just become 1/3. So they have an acceleration of G/3. Okay. So now let us see what is happening at the moment just before I stop this block. Okay. So t equal to 2 seconds almost. Okay. When I'm just about to stop the heavier block. So at that point of time, the system still has that acceleration, but in addition now, it's also got some displacements and velocities. So displacements are not so important, but at t equal to 2 minus, I'll write this. Okay. So 2 minus means just before, just a fraction of a second before 2 seconds when I hold that block. So that point of time, this is having a velocity v, this is having a velocity v, and obviously they are having the same accelerations as before. Okay. And the string is maintaining the same tension. Okay. Which, by the way, also if you require, you can always solve for the tension. Okay, so now you can see that this velocity will be what? It will be a into 2 seconds. So it will be 2g/3 or approximately 20/3 meters per second square. Oh, sorry, meters per second. Unless g's value is given, which is not the case, so we'll take it as 10 approximately. So this is the speed just before t equal to 2 seconds. Okay. Now what happens the moment you stop this block? So now let us look at t equal to 2 seconds. So you stop this block. So the moment you stop this block, its velocity becomes 0. Okay. But you've not done anything to the other block. So this is still having that velocity v upwards. And it's okay. So the string immediately slackens. Because this one has been stopped and this is still allowed to go up. Okay. You're not disturbing this block. So by its inertia, it continues with its momentum at that moment. Okay. But the other one, you have stopped this. So the tension in the string becomes 0. Okay. The thread or string slackens. So this is a very important point of view. Okay. So the moment the thread or the string slackens, now what happens? Both of them have an acceleration equal to g downwards. Okay. So after some time, what we'll see, I'll just draw the diagram alongside because we have to reference it to this one. So after some time, I'll see that this block has reached somewhere up. Okay. But its velocity v1 has become less than what that original v was. Okay. And this block would have comparatively displaced downwards and its acceleration v2. So let us say this second diagram that I'm drawing now, this one, this is at some time 2 plus delta t. Okay. So in that time 2 plus delta t, this block has made a displacement s1 and this block has made a displacement s2. So what will s1 be? It will be v delta t minus half g delta t square. Okay. Because from here to here, the first block, it is going up with an initial velocity equal to v and acceleration equal to minus g. And the second block, it is starting with an initial velocity of 0 and it's having an acceleration of g downwards. So the second block's downward displacement is half g delta t square. Okay. So now you tell me, so go through these diagrams carefully and tell me what is the condition for the string to become tight again? Okay, because you can see that from this moment onwards, the string has become slack. Okay, so now the important question is that at what time or under what condition, you can say, what is the condition when the thread becomes tight again? Can you tell me what is the condition for the thread to become tight again? Anyone? Okay, I'll give you
Sir,
a
move
hint.
it from rest.
Sorry?
Move it from rest because it was in rest now.
Nahi beta. Siddharth, your answer is correct. Okay, I'll give you a hint. You will understand. Okay. So see, in this diagram, when the thread was last tight, before I just stopped this one, what was this length? Let's say it was L1. Okay, and this length it was L2. So L1 plus L2 is the total length of the thread. Now. So if it becomes tight again, now in this diagram, let's say this length has become X1 and this length has become X2. So when it becomes tight again, your X1 plus X2 should become equal to what was originally L1 plus L2, which is the length of the string. Okay, so that means S1's magnitude should be equal to S2. Now see why it's becoming loose over here, because this length L1 is decreasing at the rate of V, but this length L2 has momentarily become at rest now, become constant because V is become 0. So that's why the string slackens now, because L1 is decreasing, but on the other side L2 is not decreasing at that moment. So the string loses tension. Okay. But by the time this block M1 has gone up the same distance, on the other side M2 has come down, the string will pick up its tightness again because the length has stretched out. You understanding? No? When the second block has gone down by the same distance that the first block has come up, that's when the string is that's when the string is stretched out to the full length. Okay. So the condition for this thing to happen, this is the condition for the string to become taut. Okay. Because at that point of time, this happens. X1 plus X2 becomes L1 plus L2. Okay. So just apply that condition now. So you can see that V delta T minus half G delta T square should become equal to this. Okay. So we get this nice relation that V delta T should be equal to G delta T square. So G delta T square minus, now substitute the value of V which I had written from here. Where is it? V was this. So V is 2G by 3. Delta T should be 0. So you'll see that obviously one solution is delta T is 0, but that is at T equal to 2 minus, just before you held that block. But the other solution is at delta T equal to how much does that become? 3 by 2 seconds, right? So this is at T equal to 2 plus 3 by 2 or 3.5 seconds. So this is when the string becomes tight again. Okay, so I think that is what you have to ask. You have to find the time elapsed before the string becomes tight again. So that will be 1.5 seconds, because from 2 seconds, the delta T further time is that much. Okay. Oh, sorry, I got it inverted. It should be 2 by 3 and not 3 by 2. The time elapsed is 2 by 3 seconds. So the total time on your stopwatch is this plus this, so it's about 2.67 seconds or whatever. Okay, so people, hope this question is clear. Especially Ashutosh, who has asked me this question.
Yes, sir, it is clear.
Okay, good. Okay, so understood the kinematics partner, that you have to see that the heavier block has to go down by the same distance that the lighter block has come up for the string to become tight.
Yeah, yes, sir. Yeah.
Okay, now let's move on to 25th question. 25th question, I think you have just missed out the geometrical trick in the diagram. Rest, it's a very simple question. So the geometrical trick is that maybe you must have thought that if the angle is not given, then how will I solve the problem, right? Was that the issue in the
No,
question?
sir, that 3753.
फिर तो हो
Sir,
गया
that
ना?
3750.
Okay, so if you understood the angle, then rest is just free body diagram. So it's a 3, 4, 5 triangle. So that's correct. It's 37 and 53. It's a right angle triangle. Because it's 3, 4, 5. So it's a right angle triangle. And this angle is how much? It is 53 degrees.
Sir, it will be 50.
So let's call this like alpha, let's say. And let's call this angle beta, which is 37 degrees. Okay. So now it's just a matter of the free body diagrams. Okay. Both the blocks are of same mass. But therefore, which one will dominate? The one on the steeper slope will dominate. No? If the masses are same, then this will dominate because the mg sine component is greater for it. So when you divide the weight into components, this will become mg sine
MG sine
53.
53.
So that's 4 by 5. Okay. Whereas this component will be mg sine 37, that is mg into 3 by 5. Okay. The other component of mg you need not worry about, but I'm just writing it for completeness. So the normal reactions will be such that this one has a lesser normal reaction. This one has a greater normal reaction. But what is more important is that the sign components, this one dominates. Okay, so we will have for the first block, let's say this is block A, this is block B. So for block A, we'll have the equation mg sine alpha minus T is equal to MA. And for the second block, we have T minus mg sine beta, and then we'll just substitute alpha and beta after adding the two equations. So mg sine 53 minus sine 37 is equal to 2ma. So A, as you can see, will become 4 by 5 minus 3 by 5 into g by 2. So I believe that should become g by 10. So what did we have to calculate? The magnitude of the acceleration. So that's it. No?
So,
Yes. Yes,
so
tell me. Yeah.
already you got to know 53 that is, and like you already knew like sine 53 and sine 37 is like 4 by 5.
Yeah.
Or
Yes. This is a standard triangle. Okay. Like if you've studied, for example, calculus with me, you will remember that I had told you that there are three, standard right angle triangles that you should remember. One is the 45, 45. That's very easy to remember. Okay. So that is 1, 1 root 2. Then the other one is the 30, 60, 91. So if this is 60 and this is 30 and this is 90, then these are 2, 1 root 3 like this. Okay. And the other is the 37, 53. So these are three standard triangles that you should always remember. Okay. 3, 4, 5. So these are the Pythagorean triplets, right? That so this one, then this one, and this one is. So you should remember this one specifically for all chapters in physics. Okay, it's very useful.
okay, so
Okay. So that is done. Okay. Now next, what we're doing is question 34. Is it? Okay, 31 also. Okay, let's quickly go through 31. So 31, you have to use a constraint relation because there's a system of pulleys. There's a combination of pulleys you can see. Okay. So we'll have to use a constraint relation. Now what is happening is that this thread is going around another pulley, and then it's attached to this point on the, on the support of the pulley. So there's actually a fixed point over here. The second point where this thread is attached is actually a fixed point. That is the main thing you have to understand in the question. Then this is attached to another block B. This side, this thread is attached to a block A, let's say. Okay, I've labeled the figure a little differently. They have taken A and B as the pulleys. Anyway, so what we will understand is, obviously we are dealing with frictionless surface here. So this block has a tendency to move in this direction. Okay, and therefore, because this is pulling it down. So after some time, let's say if this block has moved here. So this is the displacement of block B. So not this. This is the displacement of block B. And during that time, let's say A has moved here. So this is the displacement of block B. So you can see that from here, how much thread length has got reduced. Okay, when you come to the second diagram, the thread has now become like this. So the original thread length, whatever it was, okay, that has now become, from this side, you can see thread length, this branch and this branch are now gone. So it is minus 2 times SB. But here thread length SA is increased, okay, here to here. So it is plus SA. So as long as this, we know that this string is inextensible, so it does not stretch. So we know that this is the case. Okay, so differentiate this twice, and you get acceleration of A is going to be twice the acceleration of B. So once you understood this, let's say this is having an acceleration A. The acceleration of B is, let's say, A. So the acceleration of A will become 2A. And then it's a matter of free body diagram. So on this, there is T plus T, 2T acting horizontally. So we have 2T is equal to mass of B into its acceleration. And on this, we have weight minus tension is equal to mass of A into acceleration of A, which is 2A. So now solve these two equations and you will get the answer. Okay, so we hope the question is clear.
So how did you got 2A acceleration? And just say once more.
So see, you have to understand the constraint relation. So just compare these two figures. Okay. This figure, so let's say this length is L1, okay, and this length is L2. So what is the total thread length? It is 2L1 plus L2, correct? Okay.
Yes, sir.
Now when the system has moved from here, what has happened is that this block has moved somewhere here. Okay. So if this block has moved by X, then the pulley has also moved by X. No? So this thread length from here to here, this has become how much? L1 minus X. Okay. And during that time, this block has moved down by Y, let's say. So this length now has become how much? It has become L2 plus Y. So that same thread length is now equal to twice of L1 minus X on top, but the vertical section has become L2 plus Y. So if you compare these two, you can see that 2X is equal to Y. No? So 2 times dx by dt is equal to dy by dt. So if this is moving with a velocity VA, this is moving with a velocity VB. So we have 2 times VA is equal to VB, and differentiate this once more. So we have 2 times acceleration of A is equal to acceleration. But I've taken A and B opposite here now. Okay. in that diagram, just made that mistake. This was B and this was A. But anyway, so you can see that the vertically downward one has, has double the acceleration as the one which is moving horizontally. Okay, hope this is clear.
Yes, sir.
Okay, now question 33 is a very important application of pseudo force concept. So we'll discuss that quickly. So in question 33, see what is happening is that if the triangular wedge is accelerating towards the right, then on that small block placed on it, the pseudo force will be towards the left. Okay, so that's what we have to understand over here, that this is on a frictionless surface. So the moment we let that other block go, the one which is hanging vertically, because of its weight, it will start pulling this. So this is having some mass m, this is having some mass m prime, this angle is theta, and this smaller block kept over here is mass small m, let's say. Okay, now the moment we let this go, because of its weight, it not only accelerates, but it also creates a tension in this thread. Okay, so that tension is causing this block to accelerate. But if this one is at rest with respect to the wedge, okay, then what should happen is that when I make the free body diagram of that small block in the non-inertial frame of the wedge, so the wedge is accelerating at E, so there should be pseudo force acting on this, which is MA like this. Whereas the other real forces acting on it are its own weight mg and the normal range like this. Standard, if this angle is theta, then here this angle is theta and here this angle is theta. Now this is at rest in this frame, in the non-inertial. So the forces which are tangential to the surface should balance. No? So MA cos theta should balance mg sin theta. So the acceleration that the wedge should have should be g sin theta. So that's the first thing. Sorry, g tan theta. Sine by cos, so it should be g tan theta. So this is the acceleration we require, okay, for the block to be at rest with respect to the wedge. Okay. Now, once we know the value of this acceleration, now we come down to the free body diagrams of the other two things. Now, the convenient thing to do here would be to make the combined free body diagram of this plus this. The block small m plus the wedge m prime, okay, and that too in the inertial frame. So in the inertial frame, this is acting like a combined mass which is accelerating at t. And on that combined mass, the external forces which are acting are tension, combined weight, and normal reaction from the ground, which I'll write as some n naught so that it won't confuse with this n. So you can see that for this, the equation becomes that T is equal to m plus m prime T. That's my second equation. And in this, I can substitute the value of G. And finally, for the vertically hanging block, this also in inertial frame. So I have capital Mg minus T is equal to capital M. So from this now I can solve. So I can solve for capital M, which will come in terms of M prime and small m. So add the two equations, you will get rid of, that is equation 2 and 3, add them, you will get rid of tension. So do equation 2 plus 3, and after doing that, in that substitute A as G tan theta. Okay, so you'll get the value of M. Okay, so hope this is also clear.
Sir,
Hmm.
so sir, here you made the FBD of like the wedge, the smaller block, and the M.
Yeah.
Right. And so in smaller block M, you're taking that as rest or
At
accelerate.
rest, no? See, that is in the non-inertial frame. No? So in the frame of the wedge, see what's happening, it's at rest. No? See this one. This is the FBD of the smaller block, small m, but in the wedges frame. And that's a non-inertial frame.
So that's where there's a pseudo force also.
Yes, that's what this is. So you can also understand this intuitively. Na? As the triangular wedge is moving with an acceleration A, the block that is placed on it, it will experience a backward force, na? Because it's in the non-inertial frame. So if that backward force is strong enough, it will have a component MA cos theta, which is capable of balancing the MG sin theta component. Na? So that's the condition for it not to slide down the incline. Okay, so hope this is clear.
Yes, sir.
Okay. Okay, what do we have next? We have question 34 is again constraint relation problem. So I would like just advise you to try it out yourself. Okay, I will just give you a hint in terms of the constraint relation for question 34. Solve it similarly like we had done for question 31, like we did 31. Similarly, in question 34, all parts, you have to find the constraint relation. So I'm just giving you the constraint relation and try it yourself later, because there is system of pulley. So apply thread length conservation. So when you apply that, in the first part, for example, you'll get the constraint relation in, the A part. You'll get the constraint relation that acceleration of A should be twice in magnitude of acceleration of B. Okay. So you try to figure this out yourself, how this constraint relation is coming. Similarly, in the second part, acceleration of A will again be twice of acceleration of B. And similarly, in the third part also, will again be the same, that acceleration of A will have a magnitude which is 2 times acceleration of B. Or actually, in this case, when you solve, you'll get acceleration of A equal to acceleration of B equal to 0. Because they are 2 and 1 kg, so it will. No, sorry. Won't be like this. No. In fact, what you will get is that A is going down, B is going up. In this case, you'll get the same. B is going up, A is going down. In this case, B is going down and A is moving horizontally like this. Okay, so try this yourself with the constraint relation.
Okay, sir.
Then, yeah, then we come to 37th question. So 37, we come to that situation where we have a block of mass m, and on this side, a monkey is also mass m. So if the monkey just grips the rope without trying to climb or drop, both the monkey and the block will be at rest. Okay. But suppose, so if the monkey is applying a downward force on the rope, if the monkey pulls the rope down with a force F, so the tension in the rope becomes equal to F. So if P equal to F is equal to mg, then both the monkey and the block remain at rest. Because you can see on the free body diagram of the monkey, there's tension T acting, weight mg acting. On the block's free body diagram on the other side, there's tension T and the same amount of weight. But if the force is applying is greater than its weight, so that means the tension becomes greater than mg. So that means both accelerate upwards with A equal to F minus mg divided by M. So they will accelerate upwards if P is greater than mg. And on the other hand, if the monkey applies a force which is less than his weight, so it's basically climbing down in that case. Okay, so the tension becomes less than mg. So in that case, both accelerate downwards with A equal to. So in this case, both of them will be accelerating downwards. We apply the condition that T is less than mg because F is less than mg. So that's your 37th question. Okay. 38th is also a very similar type of problem. I'll just give you some idea about the free body diagram. So in 38, what is happening is you have one rope. On that there is one monkey, which is monkey A, and holding on to his tail, there's another monkey which is B. And the masses are given to us. So 5 kg. So for example, you can see that if A and B are at rest, then let us say the tension in the rope is P and the tension in his tail is T prime. So you'll see that T will become their combined weight, but T prime will be equal to the weight of B. This is the condition for them to be at rest. Okay. So in that case, you can see that the tail has tension T prime equal to 20 newtons. So definitely it's not breaking. Okay, the tail is not breaking. Now on the other hand, suppose now the monkey A with the monkey B holding on to its tail, if this starts climbing at the acceleration A, so B is at rest with respect to A. So in that case, what is happening, when you work out the free body diagrams, you will see that in the ground frame, B has tension T prime acting with respect to ground. It's accelerating at A. Same thing that A is doing. So in ground frame, both of them are accelerating at A. So you'll see that what will happen is you calculate the tension to be the sum of their masses into A plus G. And you'll calculate the tension in the tail to be mass of B into A plus G. Now you can see that T prime has become greater than 20 newtons. So condition for the tail to be intact is that the tension should not exceed 30 newtons, or the tension should be less than 30 newtons. So you can see that so 2 kg is multiplied by A plus 10 should be less than equal to 50. A should be less than equal to 5 meters per second. So with this, you should be able to. So I've not solved out each free body diagram elaborately in this case, okay? But I think I've given you enough hint from which you can solve this yourself, right?
Yes.
Okay, now just go through this once. Let me know if there's any doubt, and then next we are coming to 39th question.
Sir, I got to know like how to solve the 39 and the 41st.
Okay, very good. That's done then. Okay. So now I'm moving on to some other questions. I think most of them are, some of them are from laws of motion only. So we'll complete these first. Then we'll come to the kinematics doubts. So I have some questions which I'll put up on the board. There shall come to your questions also. Okay, so Mansi, I'm starting with a couple of questions that you have sent me.
Okay, sir.
Then I'll come to your questions, Janvi. So you have this kind of a structure, which is made of a wire frame kind of thing. So this is a fixed wire frame, okay, but it's a frictionless wire. Okay. And we have, let's say, something like a ring that can slide freely on it. So ring slides freely on the fixed wire frame, which is frictionless, it's smooth. Okay, so a bead released from one end of this frictionless rigid wire frame fixed in a vertical plane slides periodically on the frame. Size of the bead is negligible as compared to the radius of curvature of the turns. Okay, so now this is something significant over here, that when we study circular motion in a little bit more detail, next up after doing kinematics, we understand the significance of this statement a little bit more. That they are not sharp corners, they are curved, in such that at the curve, the radius of curvature, so any curve like this has got some kind of a radius of curvature. We drop to tangents and to normals. So this radius of curvature is very large compared to the size of the ring. So that is the point of it. Okay. So it says that the size of bead is negligible as compared to the radius of the turns, which is in turn negligible compared to the length of the straight portion of the frame. If linear dimensions of the frame are made 4 times, by what factor will the frequency of the motion change? Okay. So let's try to understand this. So let's say these are symmetrical. So these are L each. Okay. And this is, let's say, L prime. So let's take the first part of the motion to get from here to here as T1. So what is the relationship of T1 with respect to L? Let's try to understand this. Okay. So as the bead slides, it will have an acceleration which is kind of like G sine theta. Okay. So T1 will be equal to square root of 2L divided by G sine theta. Is clear, Mansi?
Yes, sir.
Okay. Now let's say it reaches here at some time T1 plus T2. So that means it took a time T2 to go from here to here. So that T2 will be how much? It will be L divided by T1. Sorry, L prime divided by T1. Sorry, L prime divided by some V. So that is V1. So that V1 is the same speed more or less as it is having here. So V1 is equal to how much? It is root 2 G sine theta into L. Okay. So our T2 is equal to, like, 1 by root 2 G sine theta into this factor L prime by root L, like this. Okay. And now when it reaches this point here, and again just about comes to rest, because it's all symmetrical now. So the time taken to go from here to here will be the same as the time taken to come down. So what will be the total time here? It will have become T1 plus T2 plus another T1. Okay, is this point clear, Mansi? Just from symmetry, I'm saying. The
Yes.
ascent. Okay, so the total time period of oscillation will actually become double of this because it goes back the entire journey. So it will become double of T2 plus 2T1. So it will be like 2T2 plus 4T1. So now let's see what the relationship of this is. Okay, so this is equal to 2T2, which is like this factor L prime by root L plus 4T1, which is, like, again we can write this as root 2 upon G sine theta, because that's just a constant factor, into root L. Okay. So now what I'm trying to show you is what the relationship of this time is with respect to the two lengths. Okay, so far clear, Mansi?
Yes, sir.
Okay, now let's say the new time period will be T double prime when I replace L with 2L and I replace L prime also with 2L prime. That's it, or I'm making it 4 times.
Yes, sir.
4 times, sorry. Okay, so not 2 times, but 4 times. Okay. All right. So each of the dimensions is quadruple. So इसको भी 4L कर दे रहे हैं, इसको भी 4L prime कर रहे हैं. So the new time will become 2 times upon square root of 2G sine theta, okay, into L prime, which is replaced with 4L prime divided by root 4L, okay, plus the same thing but into root of 4L. So now we can see, comparing this with the above, now you can see that this time is 2 times the earlier time. Right? Is this clear, Mansi?
Yes, sir.
Okay. So yeah, it's a bit of a tricky question because you have to use combination of Newton.
Sir, I'm not able to hear you.
issue with your network connection, Beta? Because
Yes, sir. Now I can hear you.
yeah, okay. So don't worry, I'm recording the session and I'll send you the notes also. Okay. Yeah, so now you understood now. So I have basically divided the motion into one part where it's accelerating, then another part where it has uniform motion, then the third part where it's decelerating, and then that whole part repeats. So again acceleration, then again uniform motion, then again deceleration. So that's how we have calculated the relationship of the total time with respect to these lengths L and L prime. And this relationship is showing us that it will double when the lengths are quadrupled. Okay, so hope this is clear.
Yes,
Okay.
sir. What I did not understand initially was what the question meant by the frequency of periodic motion.
Acha. Now
Relative to what actually? Is it given a certain time or what exactly? So now it's clear.
So frequency actually kya hoga? It is like inversely proportional to time period. No? Frequency is like number of repetitions per unit time. No?
Yes, sir.
You understanding?
Yes,
No?
sir. So
So
I was confused with what unit time I had to consider.
okay. So now you understood, no?
Yes, sir.
So for example, if the whole cycle was taking 20 minutes earlier, okay, that means per hour it would be making 6 cycles. It would be making 3 cycles. But now when we quadrupled it, the time will be 40 minutes. So then per hour it will be making half of the number of repetitions. So its frequency will become half because the time has doubled.
Yes, sir.
Okay. So frequency and time period have this inverse relationship. Frequency is 1 upon time period because this is number of cycles per unit time. Okay. And capital T is the time for one cycle. So that's the relation. Okay, let's come to your next question. Okay. So this also looks like a constraint relation type of problem. So let me try to explain the question with a diagram. So it says that a horizontal plane with a coefficient of friction. Achha, you have started friction, no?
Yes, sir.
Okay. So you have a horizontal plane which has a given coefficient of friction K. It supports two bodies. One is a bar and the other is an electric motor with a battery on a block. Okay. So one is just a bar and one is a block which has an electric motor. The thread attached to the bar is bound on the shaft of the electric motor and all that. Okay. So let's say if I draw this in 2 dimensions, my diagram is looking like this. The one hand I have a block with an electric motor whose shaft is, let's say, vertical like this. So this rotates, the shaft rotates. So therefore any thread that is wound around it, it will be pulling on that thread. Okay. And on the other side, the thread coming out is attached to another object which we are calling it as a bar. So this is the situation. Okay. So this is a motor with a shaft and all that. So 3-dimensionally this is like this. This is on a horizontal plane, and this bar is attached to a thread which is going around the shaft of that motor, which is kept on another block which can move. And this has a coefficient of friction equal to K. Okay, so the distance between the bar and the electric motor is equal to L when the motor is switched on. The bar whose mass is twice as great of that of the other body. So this is 2m. This whole thing is of mass m. Starts moving with a constant acceleration. So why it starts moving? See, because when you put the motor on, the shaft of the motor or this cylindrical thing on which the string is wound, that starts rotating. No? So it starts winding the string. You understanding, Mansi?
Yes, sir.
So as it starts winding the string will become tight. No? It will develop a tension. So that tension is pulling this with some acceleration equal to W, let's say A1. So we have to find what acceleration this will have, if at all any. Okay. So now you can see in the free body diagram of this block, there will be friction. Okay. There'll be its weight and there'll be normal reaction. And this friction will be how much? It will be equal to K into N1. And similarly on this, there will be weight, normal reaction, let's say N2, and friction F2, which will be K N2. Clear so far, beta?
Yes, sir.
Okay, so now your T minus F1 is this mass into W. Okay. And on the other side, T minus F2 is this one's mass into the unknown acceleration. Okay, so from this equation, you can see that T minus K into 2 mg, because N1 is equal to 2 mg, is equal to 2 mW. So this is telling me that the tension is equal to 2m into W plus kg. So now in this you substitute. So T minus K mg is equal to Ma2. So substitute this value of T. So you get 2m into W plus kg minus kmg is equal to Ma2. So A2 will come out to be something like this. 2 W plus 2k minus k. So plus k. Okay, is the method clear, beta?
Yes, sir.
Okay, so that's your questions now. Janvi, I'm coming to your questions next.
Yes, sir.
Achha, this thing, this actually in this example that you sent me now, I don't know why it's expressed in such a complicated way. The constraint relation is actually very simple. If you go for the thread length conservation, you'll see that you
Yes,
get
sir.
it
That
quite
thing I
easy.
understood. So this is just an example of how the thread shifts, and then
I'll explain.
yes, sir.
So your question was specifically about the constraint relation only, no? In this kind of situation.
No, sir.
How to
Okay.
solve the
More
whole
of I'm
thing, the
not able to
acceleration.
visualize.
We can solve it as a problem also. We can take it like an acceleration problem also. So let's give the two masses some values, okay, and the angle also some value. And convert this to a numerical problem also. Okay. So let's say this is M1, this angle is theta, and this block kept here. This is M2. Now this is our thread, which is attached to some fixed vertical wall like this. Is also on some smooth horizontal surface like this. Okay. So suppose it is given to us that, let's say M1 is maybe 10 kgs, M2 is let's say 2 kgs, and the angle theta is let's say 37 degrees. G is 10 meters per second square. So I want to find the accelerations both in terms of magnitude and direction. Okay. So what we'll understand here immediately is that because of the mg sign component, this will tend to slide down. Okay, and the moment this slides down, this will go like this. Okay, so if this has an acceleration even like this in the ground frame, this will have an acceleration which I will call as AR, which is the relative acceleration. AR is the acceleration of the block M2 relative to the wedge
Okay, sir.
M1. Okay, because see in ground frame, I don't know the direction of this one's acceleration, because in ground frame what is happening is that one moment your system is like this. Okay. Now next moment what has happened is that this block, this wedge has shifted somewhere here,
Yes, sir.
and this block has shifted somewhere here. So its direction of motion is actually something like this. Its direction of motion is something like this. It's not like this. Okay. But yes, to the guy who's standing on this wedge, to him it will look like it's shifted like this. So that's why the relative motion is in this direction. Okay. So that's the first thing. Okay, now the other thing is the constraint relation. So before that, let's mark out all the forces. Tension, then there will be an interactive normal reaction like this, equal and opposite action reaction pair, and of course apart from this there are the weights and all that. Okay, now constraint relation, see what is happening in this original diagram. Let's say this length was L2, okay, and this length was L1. So now this wedge has moved by a distance x1, let's say. Okay, so the thread length on this side has become L1 minus x1. Okay, and this has moved like this. No? So let's say this has moved by some relative displacement xr. So this thread length has become how much? It has become L2 plus xr. No? So L1 minus x1 should plus L2 plus xr should be equal to L1 plus L2. Is clear,
Yes.
Janvi? Okay, so that tells me that the relative displacement of the block in the wedges frame should be the same as the horizontal displacement of the wedge in the ground frame.
Yes, sir.
This is the displacement of M1 in the ground frame or the inertial frame, whereas this is the displacement of M2 relative to the wedge. Okay. So basically in the non-inertial frame. So that's why when we double differentiate this term, we'll get A relative is equal to A1 in magnitude. So that's our first equation actually. That's our constraint relation. Understood now?
So there's always some cost term.
नहीं cost term that's what I'm telling you. But यहाँ पे cost term नहीं रहेगा ना, because see theta is not playing any role in the thread length. You understanding now? When the cost term comes, when the theta is variable. You understanding? That's a different situation.
Even in this thing, sir, they've given that the segment 2, which is from the pulley till M2, and from the wall till the first pulley,
That's
they've
what I'm
taken a
saying now.
segment 1.
Whatever book you have taken it from, they have unnecessarily expressed it by trigonometry and it's made it very lengthy. But the final result that they will also get is the same, that the x relative is equal to the capital X of this one only.
Sir, I can send you the photo. Maybe I have got it wrong or they've got it wrong.
Any, see, they have expressed small x as capital X cos theta. All that is fine. Okay. But ultimately, the result that they'll get in the constraint relation is that small x is equal to capital X only.
So before that, also I've sent you a picture. Can you explain that?
That picture, what you're asking is not clear to me, na, beta.
So what should
That's
be the minimum force applied? What should be P so that the block starts to move up?
You are applying a force. So this question you don't need it solved right now from here for finding A1 and A
Sir, I
relative.
just have trouble with the constraint thing.
Okay, but you understood what I'm explaining about the constraint here, no?
So this thing I got, but that thing is
See,
confusing me.
it's very simple. If the wedge moves by 1 centimeter, let's say. So if this moves by 1 centimeter, then this thread length has reduced by 1 centimeter. No? So on this side, the
Yes,
thread
sir.
length has to increase by 1 centimeter. No? So relative to this, if the block was here, this should have moved by 1 centimeter.
Yes, sir.
Okay, so very simple constraint relation. Okay. Okay, now let's come to that question, the other one then. So this, I'm assuming this is a fixed inclined plane or a movable one?
So fixed.
Fixed inclined plane. Okay, so it's a fixed inclined plane which has a fixed wall over here, and you have this block of mass m. Okay. Now to the block you've attached a pulley, and the pulley has a thread around it where one end of the thread is parallel to the inclined plane, the other end of the thread is over here, which is the end P. And now I'm assuming that we are applying some force like this.
Yes, sir. P is the force.
So P is the force. Okay. So in my diagram, let's say F is the force and P is that point. So we have to find the minimum value of F so that this block moves, no?
Yes, sir.
Okay. These two thetas are the same here. The inclined theta and this one, or they're different?
Yes, sir.
They're same.
So it doesn't much matter. I'm just trying to understand how F
Okay.
will affect the motion.
Okay. So see, tension, right?
Yes,
So
sir.
any point in a thread is what sort of a point? It's a massless point.
Yes,
So
sir.
the net force on that point should be zero, no? So whatever force we are applying, that becomes the tension in the thread, first of all. Okay. Now you come to the FBD of the block, and remember this thing is attached to the block. Okay. So there is one tension acting on it like this. Okay. And one tension acting on it like this. Okay. And then of course there is the true weight of the block, mg. And there's some kind of normal reaction that is like this. So now when I represent this as a point mass, okay, this is the direction of the incline, and this is the direction normal to the incline. With all the resolution and all that, you will see that there are two tensions acting. There's one tension acting like this. There's one tension acting
Yes,
like
sir.
this at an angle theta. Correct?
So that all I can
And
do.
then there is mg sine theta, right? Mg cos theta. Now
And
just
then
apply the condition. Okay. So for example, if your t cos theta, sorry, t sine theta becomes greater than mg cos theta, then the block will actually lose contact with the ground.
Yes,
So
sir.
I want n to be greater than equal to 0. In fact, greater than 0, even equal to its losing contact. So for that, I have a condition on t also. T should not exceed something. So this shows me that t sine theta should be less than mg cos theta. Okay. And on the other hand, if I wanted to accelerate like this in this direction, so for a to be greater than 0, the condition is that t into 1 plus cos theta should be greater than mg sine theta.
Yes, sir. So my question is,
Now
this
in
was a
this
question
case, if
actually.
this
How will
starts
it move?
moving, if this starts moving, now there's a very interesting constraint relation. If this starts moving with some acceleration a like this, then the acceleration of the point p will be how much? That becomes very interesting. Okay. So what will happen is that, see, this pulley is attached to the block, no?
Yes, sir.
So if the block is, let's say, if the block is moving with an instantaneous velocity v in this direction, okay, then this thread length is reducing at the rate of v.
Yes, sir.
So this thread length should increase at the rate of v.
Yes, sir.
Okay, so it should have a component of velocity v like this with respect to this. Okay, so in the ground frame, what will be the net velocity of the point p? So this is relative to the block. Okay, so see,
So,
if you're standing on the block now, what you're seeing is that the wall is coming closer to you with a speed v. No? So this thread length is reducing at the rate of v. So this point should go away from you at the speed v, so that that length is increasing at the rate of v. So in the ground frame, the velocity will become the vector sum of this v, okay, plus the v of the block, become the vector sum of these two. So this will become the net velocity of that point. So this velocity of the point p will be 2v cos theta by 2. As a constraint relation, it will become like this.
but so thread length will increase only with V.
Thread length is increasing at the rate of v on this side, yes, because the pulley is also moving. No? So again, see, this point is moving at a velocity vp like this, but this pulley is also moving, no? With respect to it. This pulley is moving at a rate of v like this. No? So in this one's frame, only this length is changing. No?
Okay. Okay.
Understanding? No? This is the velocity of that point p in the ground frame. It is the velocity of the point p with respect to the pulley plus the velocity of the pulley. So naturally, this is the difference of these two.
Then sir, what does this V 2V cos theta by 2 actually mean?
It means that the instantaneous velocity of that point is this much, and it's at an angle of theta by 2 with respect to this. You understanding? So as this is moving, see, as you are seeing the block moving like this, okay, and as you are seeing this block moving like this, and the thread is oriented like this at an angle theta, what do you see the point P moving as with respect to the ground? You don't see it moving like this. You will see it moving like this. Understanding? With the magnitude of velocity, which is, so it's neither moving parallel to the inclined plane, nor it's moving actually along the thread. It's moving along the bisector of those two.
Okay. Okay, sir.
So instantaneously with respect to ground, if you trace the motion of that point P, you'll see it moving along that bisector between the two threads at theta by 2 with respect to the incline, and with a magnitude of speed which is 2v cos theta by 2. Whereas if you're standing on the block, then you will see the point P moving along that thread only at a speed v. Is it clear now, Vita?
Yes, sir. Okay, sir.
Okay. Achha, one thing I'll tell you is once we discuss about relative motion in kinematics now, some of these things will become clearer.
Sir, we
Some of
have.
them, I mean, yeah, we just started with the basics, but you know,
Achha. Yes, the relative
Yeah.
part I've got actually, but the part before that, that's giving me some trouble. I think I've read too much and I'm confusing myself now.
so now try to connect it what you've learned in relative motion. Okay? The confusion will go. Okay, so that is that. Now, Pratyush, I will come to your questions also. Just a bit of time. Darsh, I'm trying to go through one of your questions. Okay, so I will share a question that Darsh has sent me. Let's go through this. So all the surfaces are smooth, okay, and the blocks all have the same mass. So this is actually a triangular wedge which is of mass m. This is a block, there's another block of mass m. So what will happen to C over here? Darsh, can you tell me this? What do you expect happening to C, the block C? Should it be moving or?
Sir, C should remain stationary.
Yes, C should remain stationary because uspe B will be applying some normal reaction like this. So let's say that is N1. So the wall will apply some normal reaction, the ground will apply some normal reaction, and its weight and all these things will get balanced. Okay. Okay. Now, what do you expect for the block B?
Block B will accelerate down the wedge.
Yes. Okay. So block B's direction of motion will be down the wedge like this. Okay. And on block B, the forces will be, there will be a normal reaction acting from here, which A is applying, let's say that is N2. There will be a normal reaction that this is applying, let's say N1, and there will be its own weight like this. Okay. So we can make an FBD and solve for B. Understood now?
Yes, sir.
So for B, my FBD will have all these forces, N1 acting vertically downwards, sorry, N2 acting vertically downwards, okay. N1 acting at theta to the horizontal, vertical, okay. And mg also acting like this, okay. The masses are all the same. So if this has an acceleration A like this, AB, what is the net force down the inclined plane? It will be N2 plus mg's sine component. Correct? No?
Yes, sir.
See, this equation makes sense, right? So this is my first equation. Now you see it's got how many variables? It's got two variables, AB and N2. So I need at least one more equation. So that brings me to the block A. Now the block A has a very interesting situation. How do you think A moves?
Sir, vertically downwards, right? Because there's no friction, so it will just go downwards.
So interestingly, if I see in the ground frame, if I see an inertial frame, then I'll see block A moving downwards. Okay. So now tell me something else. What if I'm standing on B? So I'm in a non-inertial frame. that is going with an acceleration AB like this. Here, what do I see? A moving as?
It will go to the right.
Yes, very good. It will move in this direction. So I can also use this. This is A relative. So I can use either way. So whether I take this FPD or I take this, okay. So if I take this one, for example, in this case, what are the forces acting on A? There is its own weight, mg. Okay. Then there's the normal reaction, which will be N2, because N2 is the interactive force between A and B that we've considered. Okay. And there will be pseudo force. Now, pseudo force will act in which direction? It will act like this. This will be my pseudo force. Understood? No? And under the action of these forces, this will have an acceleration which is like this. A relative acceleration is like this.
So the pseudo force will act at an angle or
Yes, it will
horizontal.
act at an angle. No, beta. See, why it will act at an angle? Because the frame is accelerating at an angle. No?
Okay, yeah.
This is your acceleration of the frame. No? So the pseudo
Yes.
force will act opposite that. No? In fact, this angle will be theta. So this is an easier equation because see, it directly gives me N2. And I needed to solve N2 no? So that I can substitute an equation 1. So in this FPD, the vertical forces should be balanced. But that
Yes,
includes your pseudo force. No? So what is the equation? That N2 plus MA2 this frame, no, there's this acceleration A which you're seeing no, of A in the ground frame. That is actually the vertical component of B's acceleration. Because A and B are moving together. No?
Sir, actually, I couldn't hear anything after N2 plus MA2. Like after that, I guess some network problems.
N2 plus MA2. Okay.
The equation you have highlighted in green.
Equation 3 is clear. This one.
Yes, sir.
So when you substitute this here, you'll get the value of AB.
Yes, sir.
So that's done. Okay. So all the normal reactions anyway you're getting by solving this. Okay. But and you'll get AB and all that also. Okay. Now, if you want to solve the acceleration of E in the ground frame, that vertical acceleration, you'll realize that A and B are moving together. No? They're not losing contact. Okay. So look at this vector diagram that I'm drawing right now. Now this makes sense.
Yes, sir.
Okay. So acceleration of A should be equal to how much? It should be equal to AB sin theta.
Sir,
Okay.
sir, can you
So
explain
hope this is clear.
last part once more?
See, A and B, they are moving in such a way na, that vertically there is no displacement between them. Na?
Yes, sir.
Their relative displacement is only horizontal. Na? So vertically they should have identical motion. Na? So their Y component of acceleration should be the same.
Yes, sir.
So that's how I got that relation.
Okay. Yeah, got it.
Okay.
Sir,
Yes.
I sent you another figure. Could you explain that one?
Yeah, I'll try to come to this. Yes, Rijita, you have some question, beta?
Yes, sir, I sent you.
Okay. Let me try. Okay, but before that, there's one more question which I want to discuss, which just a moment. Okay. So ball is thrown upwards at an angle 30 degrees to the horizontal and lands on the top edge of a building that is 20 meters away. How fast was the ball thrown? Okay. So the basic diagram is something like this. this is 5 meters above. So this is 5 meters. Okay. And the throwing point, this is 20 meters away. So if we project at an angle theta equal to 30 degrees, the trajectory should be something like this. Okay, the diagram is making sense.
Yes, sir.
Okay, now what's the easiest way to solve this? See, nothing about time is mentioned in the question, nor time is asked. So easiest thing you should do is solve by equation of trajectory. Okay. So this one's equation you take as y is equal to x tan theta minus half gx square upon u square cos square theta. I'll use it like this because theta is known and u is unknown. So instead of r, I'll solve it in terms of this. Now this point's coordinates, if this is my y-axis and this is my x-axis, so this point's coordinates are what? They are 20, 5. Okay, so it should substitute here. So 5 should be equal to 20 tan theta, which is this, okay, minus 5 into x square, that is 20 square divided by u square into cos square 30. So cos square 30 will become how much? 3/4. Correct. So from this you can solve for u. Okay, hope this is clear, beta.
Sir, actually, I did the same way, but my answer wasn't matching. I was getting some irrational answer, but the answer key said 20 meters per second.
20 looks unlikely. I mean, you can substitute this thing. So anyway, let's try to insert this. So this will be how much? This will become 20 cube, in fact, by 3u square. Correct. That will become 20 by root 3 minus 5. So write this as so u will become square root of 20 cube upon root 3 into 20 minus 5 root 3. So definitely doesn't look like you can get a answer like 20.
Sir, I got the right answer for this, sir, and I also use equation of trajectory only.
Okay. So this is so just substitute root 3 as 1.73. No? Where is this question from?
Sir, the projectile motion assignment.
Assignment, no? So the answer will be correct then. Okay, just check by taking root 3 as 1.73. Okay.
Okay, sir.
Yes, sir, it's correct.
Okay. So this is the method only. Okay, this is only the method of solving it. I mean, this is the easiest method. You can also involve time-based equation and solve.
Yeah, sir. I used this, but like I just wanted to confirm it because I wasn't.
Oh.
I was getting an irrational answer that.
Okay. 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 So people, there are still some doubts pending. Particularly Pratyush, your doubts module of kinematics. Okay, and Srijita and Janvi, you have also sent a couple of doubts. So Pratyush, your doubts from the module of kinematics I'll be discussing in the next kinematics class. Okay, so don't worry about that. We will discuss each and every module doubt before we move on from kinematics. In fact, in this week I'll try to solve all the doubts. And Janvi and Srijita, I'll solve your doubts also. I'll either send you some hints or if required, we will have some doubt session again in the week. Okay, people.
Sir, it's just this concept. It's giving a lot of trouble, and sir, most of the questions are on this only.
Okay. So I'll just go through it and help you out with it. Okay.
Okay, sir. Okay.
So
Sir?
thanks for attending. Wish you all the best, people.
Thank you, sir.
Sir,
Thank you, sir.
Thank you, sir.
Okay.
sir, can you hear me?
Yes, Shrita, I can hear you better. Tell me.
Sir, I had some doubts in HCV, but I got disconnected. Can you please share the recording?
Yeah, I will share the recording and the notes with it. Okay. And if some of
Thank
your
you,
doubts
sir.
are not clear, I will help you out with it. Okay.
So,
But we have done mostly NLM doubts today. We haven't done kinematics doubts from HCV. Okay. Yeah.
so like if the value of G is not given, we have to take 9.8, right?
See, generally in HCV, you have to take 9.8. But for example, in the module questions, you have to take 10. And
Sir,
in
but like
any,
that assignment you had given for 1D motion, like we had to
that you
take 9.
take 10. You take 10 with it.
Sir, in the assignment, because mostly answers are coming accurate only when taking 9.8.
Yes,
But
sir.
the answers are in decimals. So like there's like when I took 10, it was something around 3.5, and with 9.8 it was 3.1. So like that much.
Yeah,
difference.
okay, so that question must have been taking this as 9.8 into account. Okay. But generally what happens is the assignments I give, the value of G should be given. Otherwise, okay, you can take either 10 or 9.8. But anyway, at the exam level, don't worry, you will be given the value of G. Okay.
Okay, sir. Thank you, sir.